Hi, it's Robin. Way back in September 2019, I made a video called C64 Joystick-Controlled Sprites in Assembly Language and Basic. In that video, I had said I would make a follow-up video about a more advanced assembly language example, but I never did get around to doing that. Until now. So if you haven't seen the original video, it's probably best that you check that out first. That video was actually the origin of the Making Lamers reference. So if you don't know what I'm talking about, definitely go see that. Anyway, I'm back at it. I'm going to try and make more lamers. So I'm going to load up Turbo Macro Pro. Check the video description for a D64 file that'll contain the Turbo Macro Pro assembler I'm using and also the latest version of the source code for this example. I'm using the micro IEC for my disk access and the Super Snapshot cartridge, but neither of them is necessary to run this. And this code also doesn't require the REU version of Turbo Macro Pro, so you don't need a RAM expansion unit or anything. Okay, once the assembler is loaded up, sys 32768 to start it. And then back arrow load. Sprites 21 is the latest version of the code. You can use back arrow star to list the disk directory in case I update the file with an improved version that fixes a bug or whatever. Okay, and there's the source code. Shift F8 jumps to the bottom of the file. And you can see right below the cursor L308, 308 lines of code, and we'll be going through that today. F2, or that's Shift F1 to jump back up to the top of the source file. Back arrow 3 to assemble. And S to start. And again, we'll just take a quick look at it. I showed this in the previous episode, but basically you can move the sprites around. If you press the fire button, it changes the color of the current active sprite. If you press numbers 1 through 8, you can choose that sprite number. So I'll press 2, and there's B, 3 is C, and so on all the way up to H. And if you press letters A through Z, it will change the currently selected letter to whatever you like. So we'll choose 4, which is that purple D. You can change it to pink or light red, and then change it into an I or whatever. Now, the only reason this code is as long as 300 lines is actually because those sprites are generated with code. So we'll look at that too, even though it doesn't really have much to do with the main point here of reading the joystick, moving sprites, reading the keyboard. We'll take a look at that code too. It's actually kind of complicated. Okay, I've got it set up, so just hitting restore sends you back into the assembler. Okay, and we're just going to walk through the code. So this first definition is ZP1. That just stands for 0 page 1. And it's just a pair of bytes. Usually I label it like this, FB and FC. It points to the first byte. And I often keep a couple spare 0 page locations free. Commodore Basic actually makes these ones available. FB, C, FD, and FE. I think I've shown that in some previous videos. I don't give them more specific names because I use them for various purposes in a single program. And V, just like in the last video, V equals 53248. That's also in hex. That's D1000, D000. And that's where the video chip is in memory. So these labels just make the source code a little bit more readable rather than using constants in the code. Star equals 4000. That's where our program will assemble in memory to. And there's nothing special about 4000. I used it because it's just after where we'll be keeping the sprites today. These next 3 lines just load 0 into the accumulator and then store it in both the border color and the background color of the VIC. It's just setting the screen to black. Then This is the PETSCII code for clearing the screen. So we just load it and jump to subroutine FFD2, which prints a clear screen and clears the whole screen. These next 4 lines put the low and high byte of 32768, which is where Turbo Macro Pro lives in memory. That's also 8,000 hex. I'm using decimal just because we use that same sys 32768 to start the program. And we store it in the NMI vector. That's what allows us to just tap restore and re-enter the assembler at any time. This is a great trick for development, although you should remember to delete these lines before you ship a game or whatever using this, because otherwise you'll just cause the program to crash when the user hits restore. We've got a number of subroutines here, and we'll look at these in more detail later, but after the program sets up here, then it's going to generate those sprites, Makesprites, and we'll look at that later. And also Initsprites, which sets up all the various Vic pointers and so on to display the sprites. And then we have a forever loop, and this is just an endless loop. So that's why I labeled it forever. And there are 4 subroutines that are called over and over again. This is the main loop of our program. Pretty much any program has this kind of main loop running in the background, where we first read the joysticks, then we read the keyboard, then we'll position the sprites, then we'll wait for the raster so that the program is synced with the video update, the video display, and then we jump back to forever. So these 4 subroutines will run over and over again. I think it's usually nice to make a main subroutine like this, even though these jump to subroutines cost a few cycles. It's just so much tidier and easier to see what your main program loop is doing. So basically the rest of the program is just these 6 subroutines. So we'll look at them one by one here. The first one is initialize sprites. This sets up the various VIC video pointers to display the sprites. So the first one is we're going to turn on all the sprites. We're going to load it with 255. Again, I'm going to use more decimal than usual here today because this is tied to that first video that gave a basic program and then converted it to assembly language. So I'm going to use a bit more decimal than I normally would here. Of course, you could use, if you wanted to use FF hex, that's fine. But we'll just use decimal in keeping with the basic origins. And we'll store that in register V+21, which is the sprite enabled, disabled. All 8 sprites each have a bit in there. And if it's set to 1, that means the sprite is enabled, 0, it's off. Now we're going to set the sprite pointers. I don't know if this is more convoluted. Like I said, I wrote this code a long time ago. Not that I was no good at programming then, but you write something, and then you look at it later and you think, why did I do that? I don't know. Anyway, not necessarily everything here is going to be the best code I've ever written, but overall I tried to write it for legibility and comment it fairly well. The sprite pointers we're using are from 192 and up. So that's actually the same as 192 times 64 decimal is equal to 1288, I believe, or 3000 hexadecimal. So it's just saying that the first sprite is going to be using sprite pointer 192, which means its sprite definition starts at location 3000 hex or 12288 decimal. And we have a second index here, loading y with 0, and we're going to use that as an index through the sprite pointers, going through all 8 of them. So we're going to transfer x into A, and then store that first sprite pointer. So sprite 0, this is the location for sprite pointer 0, and we're going to store 192 in there, adding y, which is currently 0, to the memory location. Then we increment both x and y to point to the next location, and we keep doing that until y is equal to 8. That would indicate we've set all 8 sprites. it'd be possible to do some math to avoid using one of these index counters. I don't know. This might be more readable. And then we have a very similar routine to set the sprite colors, where we're going to set the first sprite to white, and then so on, red, cyan, purple, green, blue, yellow. And again, we're just going to transfer it in, store it in the series of sprite color registers until we've filled all 8 of them. So this is just initializing the sprites. This could be done other ways too. And we're going to set this one memory location, like a variable sprite number, to sprite 0, so that initial letter A is the active sprite that the joystick controls. And that's the end of that first routine. Next we have Readjoystick. Here we're going to load that sprite number that we just set, initially 0, into the X register, and that's so the same code can control any of the 8 sprites. Then we load 56320, which is joystick port 2, and we shift it right so that the low bit of the joystick falls off into the carry. And then we can examine that bit with the branch of carry set. This is actually a lot quicker. Last time I showed you to load the joystick and then AND the bit with like AND 1, AND 2, 4, 8, and then compare. This is actually a little bit more efficient to load it once, shift it off, and then check the carry. And if carry is set, that means that up is not moved, so we can jump ahead to down. If up is pressed, I said moved, if up is pressed upwards, then we're going to decrement the Y position index by X. This way we can handle all 8 sprites, as I was saying, with just one routine. If X was 7, then it would move sprite 7, if they're numbered 0 through 7. And then likewise, the next bit is for down. So did we move down? Is the bit set? Yes, then we branch ahead. If it's no, then that means we're pushing down, and we can increment the Y position. Left and right are very similar, but a little bit more complicated because, as we talked about in the previous episode, we need 9 bits to represent the sprite X position. So again, we check, is the joystick left being pressed? If so, we decrement the X position, and then we have to check it. We load into the Y register because A is busy holding the joystick position, or the joystick register. We load into Y, and we check, did we cross over into the 9th bit? If so, we also need to decrement the X position high byte, which we're storing in another table here. These are each 8-byte tables, and we'll look at them at the end of the program. And here, finally, we can check right. That's a little simpler because we can just check if it's wrapped around from FF hex to 0. We can just check that with a single compare. We don't have to do this extra checking for FF. Now we've checked all 4 joystick directions. We have to check if the button is being pressed. So once again, we've been shifting what's in the accumulator off into the carry bit by bit. And this is the final step. We check if the button is pressed. If it's not pressed, then we check for this bounce. I call this routine bounce as in debouncing, so that when you press the fire button, you only get 1 color change per press. I don't think it's really the right use of the word bounce, but sometimes when you're coding, you just don't feel like sitting there trying to dream up exactly the right label. You just want to keep writing your code. So I think that's what I did here. But essentially, I set a flag. If you have pressed the button, then we set a flag, and then we wait for the button to be released. And then if it's done both of those things over multiple frames, checking it, and then waiting for another cycle and releasing it, then we increment the sprite color. Again, indexed by X. So that's just so that if you just press the fire button once, it doesn't change the color like, 100 times. Well, it would change at least, 60 times a second on an NTSC machine. So even if you hit the fire button for a fraction of a second, you'll probably get multiple color changes. So this little check here allows it to only change color once per press. Okay, on to the next routine, reading the keyboard. So we're kind of cheating here. This is a kernel routine, FFE4, which does the keyboard scan for us. Now, sometimes I actually read the keyboard matrix directly, but in this case, just using the kernel routine is totally fine. So if it's equal to 0, then no key is pressed, and we just branch all the way ahead to exit. But if a key was pressed, then we compare it with 49, which is the PETSCII value for key 1. And if its branch of carry clear is the same as branch of less than, if the value was less than that, they press some invalid key. But otherwise, we check and we compare it with value 57, which is key 9. And if it's greater than or equal to that, we're going to branch ahead because they have not pressed one of these keys 1 through 8. So if we end up here, we know the key is from 1 to 8 with a PETSCII value of 49 through 56. We're going to set carry in preparation for subtraction and subtract 49. That has reduced the PETSCII key that we got back 1 through 8 into a number 0 through 7, which is going to be stored in sprite number, which is our active sprite. So basically all that code just to check if we're pressing 1 through 8, and if so, set sprite number to 0 through 7, and then we return. Otherwise, we're going to check if it's equal to 65, which is the A key. And again, if it's less than, we just exit. We compare it with 91, which is 1 more than Z. If it's greater than or equal to that, then we leave without doing anything. But if we get here, that means we've pressed A through Z. We're going to clear carry and add with carry. The 6502 doesn't have a carryless add or subtract, so that's why you always have to set or clear it. Set it before subtraction, clear it before addition. And we add 127 to turn the key code into a sprite index between 192, which is where we store the sprite for letter A, and whatever plus 25 for the Z. So that's just converting letters A through Z into the correct sprite index, and then we store it in the sprite index. Okay, so that's the return. We're done reading the keyboard. Next, positioning the sprites. So this routine takes those various sprite variables that we've been fiddling with above under joystick control and puts them into the VIC registers. First, we clear the SpriteX high bits. All 8 sprites have their high 9th bit packed into this one register, V plus 16. So we're just going to clear that out first. Then we're going to set the Y index to 15 and the X index to 7. X is going to represent the current sprite number from 0 through 7, and Y is set to 15 because there are in total 16 regular X and Y sprite registers, and they're interleaved in the VIC. First, sprite 0's X is in the very first VIC register, and then beside it is its Y position, then X, then Y, and so on for sprites 1 through 7. But that's a very inefficient way for us to store our variables for the sprite position, because then we can't use a single simple index of 0 through 7. So basically we've got this linear mapping in our own variables, and we've got this interleaved mapping in the VIC. Because of that, you have to choose. Are you going to represent your data the same way the VIC registers are? Well, that's nice and easy for copying our data into the VIC registers, but the downside is that all the indexing we've been doing, you'd always have to be multiplying the index by 2. Anyway, it's just a pain. I chose to do it this way. Okay, so that's why we've done that. We've got a loop here where we're going to load the Y position. So we're starting at the right-hand side and working down just because the 6502 typically is a little more efficient doing it that way. We're loading that Y position with the 7th sprite Y position and then storing that in the video chip position plus 15, which is sprite 7's Y position. Then we decrement Y, so it's now pointing at sprite 7's X register. And then we can simply load the X position, low byte, with the same comma X. That's sprite 7's X position. And then with the same store V comma Y, we can now store it in the X because we've gone from this is sprite 7's Y, we decrement it, and now it's pointing at sprite 7's X. And again, we decrement Y. So that's sprite 7's X and Y copied, the low byte of X. Now we're going to take the high byte, or actually just the high bit of the X position. Well, it's a full byte, but we're only using the 1 bit. We load that. We rotate it off into carry, then we rotate it back into that register where all the bits are packed together. And then we decrement X to see if we've dealt with all 8 sprites. If we haven't, we go back to loop and we do it again. So basically Y is stepping down by 2 each cycle through the loop to deal with that interleaved VIC registers, while X is just going down by 1 each time, because it's the linear mapping, and this V plus 16, the high bits, they're being shuffled in 1 bit at a time. So all in this one loop. Just occurred to me, maybe I could, does this work? Rotate right? Oh yeah, maybe that'll work. That's potential optimization there. Instead of having to load it and then rotate it, I think you could just rotate it directly. I guess I wasn't sure if rotate had X index option. Well, I guess of course it does. Yeah, I'm going to leave that. There's an optimization you can do at home. Okay, so that's all set. Now we've got this little Waitraster routine, which checks for raster line FF, and then it actually, once it reaches line FF, it then waits, it increments X to 0, and then again waits for a 0 and just loops there. You probably could just wait for line FF to do this raster wait, just so your code runs in sync with the screen refresh. I had the second raster line because sometimes if you wait just for FF and your code is very short, it executes very quickly, it might actually allow your code to run multiple times per frame if it's very fast, if it's not doing much. If you only wait for line FF. If you wait for FF and 0, you're forcing it to then not execute more than once per frame. Anyway, I've dealt with that in previous episodes. Okay, so that is really the whole sprite demo there, but we've got one big routine left, and it's this Makesprites, where we create those letter sprites. Actually, let's just run the program one more time here. What these sprites are is just a magnification of the built-in Commodore font. So that's the same as the regular letter A, that when you're just typing in BASIC, that's the same font. But I've expanded it by 3 times, where each pixel in that character set or that font is turned into 3 pixels in the sprite. And I chose 3 because a character is 8 pixels wide, but a sprite is 24 pixels wide, 3 times. So I wrote some code to expand them up 3 times. So we'll look at that now. Now, in a way, this is pretty inefficient code. It's very inefficient code, but it's one of those things where I didn't want to design sprites. I thought, oh, this is a neat idea. I wrote it, it worked. And I'm sure there's tons of room for optimization here, or instead of running it every time, you could save that memory out, like it generates those sprites, and then you could save that in a file, whatever. That wasn't the point here. We'll go through it. If you want to do that, that's cool. Maybe I'll do that in the future. Okay, so here we go. We'll look through this routine. This is pretty long. This is kind of going to be the toughest code we've looked at today. And I'll see if I can do it justice. So we're going to set the interrupt disable, and then here we're switching out I/O and putting in the character ROM. So here I've got my programmer's reference guide. And on page 108, there's a section called Programmable Characters. And it's a tutorial here. And particularly here on page 110, one page over, is this routine that shows you how to read the built-in character ROM and then modify it for your own purposes. And particularly line 30, poke 1, peek 1, and 251. So that is why I have done it like this. Load A with 1 and number 251. It's strange using decimal, but because this is based on some of that basic code, that's why I've done it this way. So I just recommend you read that article if you're interested in that part. Now this is strange, but this is how C64 works, is that you can put the character set, normally it's not available to the CPU, but after you do this little bit here to switch the I/O port, then the actual character set, the binary image of it, will appear at location D000, which is what we've already been using as the VIC registers. That's where the sprite registers, and well, all of I/O is really, the whole D000 through DFFF is normally where I/O is, but instead it's where the character set shows up. It's kind of weird, but what we're going to do here is set D008 into that 0 page location I have. The low byte and then the high byte goes into 0 page 1 plus 1. And that's because that's where the definition, the character definition of A will appear at D008. A is the second character in the font. The definition of each character is 8 bytes. So there's an @ symbol at character 0, and then character 1, which is at D008 here, is the letter A. Okay, so that's just going to be a pointer to the source image that we're going to expand. And now, just the same, we're going to be storing the actual sprite at location 3000, and that's going to be, we're going to put that pointer in 0 page 2. So we have 0 page 1 is pointing at the letter A character. 0 page 2 is pointing at the sprite that's going to be the blown up copy of letter A to start. And we're going to do all 26 letters, so we're just going to keep this character counter that's going to count down from 26, so we'll know when we've done the whole alphabet. We'll see more of that in a bit. And here we're also going to initialize some other counters to 0, the source count and the destination count, and those are going to be counters keeping track of all the different numbers we have going on while we're trying to do this magnification. Here's a little routine that just wipes out the memory where the sprite is going to go, just to make sure it's clear, because we're going to be doing a lot of shifting around in there. 0 is what we're going to store, just to make a blank sprite. And there's going to be 63 bytes. Yeah, or actually at 64 bytes. I guess we didn't have to do, we could have started just at 62 and left that byte, but whatever. Okay, so this is just going to store 63 bytes in a row, starting up, or 64 bytes from 63 down to 0. Decrement the Y and branch. Just very simple. Next, we're going to get the source character byte. Source count is initially 0. And we're using that in the Y index, the Y register. But we want to copy 8 bits worth of that character. So we're going to store that in byte count. I guess I want to stick with 8-byte labels. So we're going to load the source byte and store it in that source byte for safekeeping. So basically we've copied the very top row of the letter A, the top byte, which is 8 pixels worth. And now we're going to blow it up by 3 times. So we want to do this loop 3 times. Each bit is going to turn to 3 bits. If it's set, then we're going to set 3 bits. If it's clear, we're going to clear 3 bits. So we're going to shift the source byte to the right by 1. The low bit will fall off into carry. And then we're going to make, this is kind of weird, but we're going to make 3 copies of the processor status, which includes the carry bit. We don't know if carry is set or clear, and we don't really care. We're going to push it on the stack, 3 copies of it. And then we have a loop here that will pull the first of those back. So carry will either be set or clear now. We're going to load Y with the destination count, which is currently 0. It's almost like a pointer into the sprite memory. And then we're going to load the top left corner of the sprite, which is currently blank, and we're going to rotate that bit into it. And then we're going to store it, and then we're going to increment Y to point to the next byte of the sprite. Now remember, there's 3 bytes across the top of the sprite. So we're going to look at the next one. Then we're going to load it. We're going to rotate the carry into there in case there was any overflow here. Then we're going to increment and look at the 3rd byte across the top row. And then again, we're going to rotate. So it's turned that top 3 bytes or top 24 bits of the sprite into just one big 24-bit register, and we're pushing the bits into it and handling any carryover to the right. Now, there's probably more efficient ways of doing this, but when you're dealing with 3s on a computer, which is much more happy doing things by 2 or 4, this was the most straightforward way I could think of handling this. So basically we've shoved 1 bit into that top row, but we've handled all the carry because as we keep going through this, those bits are going to travel across from 1 byte to the next in that top row. Okay, then we're going to decrement X. Do we have more copying to do? Yep, we do. So we go back up here and pop another copy off the stack. So carry is either set or cleared again, and away we go. And we push either 3 0 bits or 3 1 bits into that top row. And then, are we done that all 8 bits of the source yet? No, of course, we've only done 1. So we loop all the way back up here, and again, shift the source 1 more to the right, push it on the stack again, and so on. And that just repeats. 8 times 3, 24 bits are done here. Okay, now we are done the top row, but we also want not only to expand in the X direction, but we also want to expand in the Y. But we won't recalculate that because we've already done 1 row. Instead, we will make copies of it where we're going to load X with 3, load Y with the destination count. So this is, again, that destination count is a bit of a misnomer. It's more of a destination pointer within the sprite. We're just going to load that top row that we've already generated, and then increment by 3, which will move us 1, 2, and wraps around. So that's actually moving down but just by 1 row. And then we're going to store whatever was in the top row into the 2nd row. And again, increment Y and store it into the 3rd row. And then we subtract 5, which will move us from the current position up to the next byte, which is the 2nd byte across the top. And then we do the copy again. So it's just kind of doing this copy 1, 2, 3, 1, 2, 3, 1, 2, 3, and just doubling and actually tripling that top row. And now we're done that full row. So we're going to increment our various pointers, including destination count, again, which is really destination pointer, we're going to increment that by 9 to get to the next destination row. And we check, did we actually copy 9 times 21? If we did, then we're done. But if not, we go back up and do row by row within that sprite. Okay, so once we've looped enough times, and it really is a lot, we're just done one character, then we're done one full character, we're going to go to the next one. So we increment 0 pointer 1, which is the source, the character source. We just increment that by 8 because there's just 8 bytes per character. And then here we're going to increment the sprite pointer, and there are 64 bytes per sprite. There's really 63 bytes of valid data, but they're aligned on 64 bytes, just, because computers. And then once we're done moving to the next letter, like letter B, then we're just going to decrement character count, which was 26, so go 25, 24, until it equals 0. And it'll just keep looping and doing each of those letters. Still happens pretty quick, even though you can see how much the ridiculous amount of work it is. This isn't how you should do it. Like if this was a real-time calculation, well, maybe it'd be necessary in some cases. But anyway, to just happen once when the program initializes that doesn't seem bad to me. Okay, and what do we do here? And then we just switch the character ROM, we hide it again so that I/O shows up. We clear the interrupt disable and we return. And finally, we're done that routine. Okay, and all that's left here are the various variables that we've been using. They're just bytes reserved in memory. These could be in 0 page if you want to make it run faster. I just stick them here in memory after the code. That's fine. Those are just all the different ones that we've already talked about. And then there's these tables, X position low. These are just default values where the sprites start, all in a row, Y position of 100. And then X position every 30 pixels, 50, 80, 110, 140, up to 230. Now the next value would be 230 plus 30 would be 260, but we don't have, because it's only 8 bits, we can't go past 255, so we subtract 255, we're left with 5, and then all these high bits are set to 0, except that last one, that represents 255 plus the 5 here. So that's why that 8th sprite has its high bit, its 9th bit set. And this sort of initialization, up above, some of the stuff I did here, like initializing these with all this code, I don't want to give you the wrong idea. Like, it's good to know how to do this because in certain situations you need it to be calculated dynamically or whatever. But for all that code, you could just initialize the variables to 192, 193, like for those sprite pointers. That's fine. So I could have done that for some of these other things too. But of course, as a coder, you want to know how to do it properly and not just always rely on using predefined tables for every value you have. Okay, so again, here we are. Okay, so there we are. We are making lamers. Thanks to my patrons for their support in this. Sorry it took me so long to make this follow-up episode. It was kind of daunting, actually. I hope I did an okay job with it. Okay, thanks for watching, and we'll talk to you next time.